Now it's time to illustrate a couple of other features of vectors, the kinds of things you're probably going to find yourself using a lot when you use vectors, and also to demonstrate that we can make vectors of at least one other type besides int. So here I've got a file with, I'm including vector, as I did before, and I would like to, well, I guess do task number 1 first, which is to create a vector called w with elements that are of type float. Well, let's see. So I'm going to create a vector of float. Its name is going to be w. I could do it this way. So again, as we saw in the previous video, I read this as vector of float. That's the type of w. This is the default initializer or constructor for the vector type, which sets w to be an empty sequence. If I want w to contain all of this stuff, then if I wanted to, I could add the elements one by one like we saw in the previous video. Push back 10.6, w to push back. But we might begin to notice that we get tired of this very quickly. If I want the vector to have 5 things in it right off the bat, I don't want to write 5 assignment statements. And we already know when we talked about arrays in C, for example, that it's pretty common to want to do this, to have a sequence already, to initialize a vector to contain a particular sequence, the same way you might want to initialize an array to contain a particular set of initial values. And we can do that. It turns out that we could actually provide them in the uniform initializer. And here's the first place where you have to use uniform initialization because there really isn't any alternative. If you want to set a vector to contain all of these elements, the vector has been designed to allow you to input them into the curly brackets for the uniform initialization syntax. So we've got this. And we just put them all separated by commas. If you think about a C-style initializer for this, it doesn't really make that much sense because you have to ask a lot of questions about how such an initializer would work. Although it turns out there are C-style initializers that work for some types of vectors. So for example, it turns out for this vector here, you could use a certain type of C-style initializer. There isn't one that works for all types of vectors and all possible sizes. Whereas if you use uniform initialization, you can input whatever sequence you want as the initial value of the vector just by putting it inside the curly brackets. Okay, so I've got my vector of floats, and of course they have decimal points, so we can prove that indeed they are values of type float. Now I want to print out the contents of the vector all on one line. I'm not going to do the challenge exercise. That's for you to take a look at. So I'm going to say for each floating point value x in the vector w, and then I'll print it out. Because I want them all on one line, I'm just going to print out x and then a space. And then when I'm done, I'll print out a new line. All right, so we'll start by trying that. And fortunately, it looks like everything works. I printed out every element on the same line. I'm going to skip ahead and actually do task 4 right off the bat. Okay, so task 4 is just repeat task 2. And I'll call your attention, this is just putting a bookmark for next week, that if I were to change the element type of w to be double or int or something, I have to go and change this and change this. That sounds annoying. Wouldn't that be a pain if the program were really long? If only there was a better way. Well, okay, so we'll think about that for next week. But for now, I think this should be fine. But we should keep in mind, of course, there's that usual flexibility problem when I have anything hard-coded, whether it be a number or a type, to have to worry about how I would change everything consistently if that number or type were to change as well. In the meantime, let's talk about this. So at this point, my sequence looks sort of like this. I'll sketch it sort of here. So here's W. W contains 10.6, 1.87, 11.1, 11.6, and 4.45. Okay, and those appear at indices 0, 1, 2, 3, and 4, respectively. Okay, so I mentioned in the previous video that the vector is a small appliance. The whole point of the vector is that we don't have to worry what really is going on behind the scenes. Bread goes in, toast comes out. I can add elements to the end with push back. I can iterate over it with a for each loop. I can ask it its size. I can access specific indices if I want to. And I don't worry about what's really happening behind the scenes. So I guess, to actuate that, let's do what task 3 is suggesting. Let's change the element into index 1 to equal 999. So we'll do that. We'll try running it. And sure enough, there it is. Now, I should modify index 1 here. That's now equal to 999. Great. And we don't really care what's happening behind the scenes. But I'll let you in on a secret, which is that deep down, a vector seems to have all of the same conveniences that a C array would have. I can access elements by index, for example, and every element in the array is stored in a sequence that I can iterate over from left to right. And it turns out, in fact, deep down, inside the vector, inside the protective cover of the toaster, it turns out that it is, in fact, a C-style array. But it's great for us that we don't care, because the vector wraps up around all of that with this nice abstraction that this is an array that can grow and shrink. Now, how does the vector make that work? We don't care. We just know that it does. But if you go taking a look on the internet for C++ advice, you will eventually get some sources that suggest to you that you do this. W square bracket 1 equals 999. I don't like this notation. And I will admit to you that it does work in this case. There it is. Clearly it worked. I will also admit quite freely that I really loved this notation when I wrote C++ for a long time. Until I started teaching C++, I thought this was great. I love the idea that the vector, because it's pretending to be an array, can actually impersonate the square brackets that you use on an array. I thought that was really clever. However, there is a disadvantage to using the square brackets, and it's a big one. We saw in a previous video that one of the advantages of uniform initialization is that it allows the compiler to give you an error in the event that you might have made a certain mistake. And it's great to have a compile error versus some other kind of error, because when the compiler finds it for you, you don't have to go find it by debugging. And it turns out that the disadvantage of square brackets is very similar to the advantages of using uniform initialization. So deep down underneath, the vector secretly is a C-style array. Now remember that if you want to increase the size of the vector, so currently this vector W has 5 elements. If I want it to have 6 elements, I have to use pushback. Pushback is the way that I increase the size of the vector. There are actually other ways of doing it, but the .at function and square brackets are not one of them. If I use .at or I use square brackets, I'm getting an existing index. I can't add new indices using these two features. However, what if I try? So what if, let's not use index 1 anymore. Actually, let's change this. I'm going to use the value -1000. What if I try and insert the value -1000 in index 5? Now you can stare at this and agree that there is no index 5. The first index is 0, the last index is 4. There is no index 5. It is invalid for me to attempt to use index 5. Let's see what happens if I try and set index 5. It does compile. That's unfortunate. And then this happens. Ooh. So it prints the vector out up here. And before it prints it the second time, so before we get to the second line of output, I get this strange looking cryptic message. Now, we'll actually be able to parse what this means pretty quickly in this course. We'll see it in a couple of weeks. However, if I sift through it trying to look for meaning, I will notice a few things that do seem to jump out at me. Okay, the first thing is, okay, I don't know what any of this is supposed to mean. I guess I do see the word vector there. That sort of implies range check. Then I see the number 5, and then I see something about a size, and then I see out of range. Interesting. What if I tried to set index number 4000? What would happen then? I see. Here it says, I'm sorry, 4000 is, well, there we go. 4000 is the number I wanted to use, and that's greater than or equal to something size, which is 5. So it sounds a lot like it's saying the index I passed in isn't a valid index. And then the program sort of implodes and it ends. We could see this is sort of a very typical program crashed message from the operating system. And that's a sign that my program didn't work correctly because I wasn't allowed to set element 4000. There is no index 4000, so of course I shouldn't be allowed to set it. Let's go back to index 5. So here what it's really saying is, sorry, you can't set that index, there is no index 5. And if you use .at reliably, and you get a message like this, and many of you will, it probably is because you forgot to use pushback. You wanted to add a new element, but you used .at. .at is only for modifying existing elements, not for adding new ones. What if you decided to use square brackets here? So here I'm going to set index 5 using square brackets. And we try running it, and nothing seems to happen. So there is no index 5. And when I set the element at index 5, it doesn't seem like anything bad happens, but I don't see any negative 10, negative 1000 here because the vector doesn't know that it's any, the vector as far as it's concerned still has size 5. So what happened? When I use square brackets, I get the same effect as if I were using a C array, which is to say that I walk to index 5. There's 0, 1, 2, 3, 4, I'll just walk right past the end of the array. And the operation will continue. Even if the index is invalid, when I use square brackets, it tries to do it anyway. And that means that it might go and step on some other piece of memory. And you recall from C that if you walk past the end of an array, bad things happen. And that's exactly what could be happening here. But you might stare at that and say, but I didn't get an error. Isn't that great? But you didn't get the effect you wanted either. So it didn't work either way. And this is incorrect because there is no index 5. So my question is, what would you rather have happen? It silently put up with your invalid operation but still not do what you wanted, or it give you an error at the exact moment something went wrong. Especially if your code is long, although you don't like reading these cryptic error messages, wouldn't it be great to have the language help you out? To have the language tell you that you've made that mistake. And that is why it's great to use .at. .at and the square brackets differ in exactly one way. And that is that the square brackets don't do any range checking and .at does. So if you use .at and you provide an invalid index, you will get an error. The moment that you try to access something invalid, you will get an error. The language will help you catch that programming mistake. If you use square brackets, you won't. And many people will notice that when you use square brackets, even if the result does seem to do what you want, something bad happens later because when you walk off the end of an array, undefined behavior occurs. And you'll hand in an assignment that seems to be working, and then it'll break on testing because the square brackets are being used and you're not catching a case where you walk off the end of an array. That is really frustrating. Or worse, maybe you are actually able to detect the error, so you notice your program isn't working as expected, but you don't notice the symptom of the error until 100 lines after the error occurs. You use the square brackets the wrong way once, and then 100 lines later, some bad behavior starts occurring. And that's because you damaged some area of memory and didn't need the memory again until later. Whereas if you use .at, you get the error exactly when the problem actually occurred. And so you save yourself a lot of debugging. And that's one reason to always use .at with vectors. We'll notice later in the course that there are lots of other data structures on which you can use square brackets with no trouble. But on a vector, there really is no good reason that you shouldn't be using .at whenever you want to access something at a particular index.